For this project, we compared various methods used in the cognitive science literature to improve upon reinforcement learning. We are particularly interested in comparing the DINA and pseudo-reward-based architectures. Our agent completed a simple maze task. The agent was required to find the shortest path from the starting point in the top left to the goal state in the bottom right. A reward of 1 was conferred at the goal state. Here we're watching a naive Q learner complete the task. Q-learning is a model-free method which updates a Q function of state-action pairs so that the agent moves towards states of high reward. We see that as time goes on, the Q-learner converges to the optimal path.
The plot at the bottom shows how many steps it takes the agent to get from the starting point to the goal state for each episode.
Here's a Q-learner that uses the DINA architecture. Instead of simply updating Q values as the agent moves through the maze, at the end of each step, a random number of past moves are replayed. Evidence suggests that replaying memories or simulating experiences helps humans learn new tasks more efficiently. The DINA Q-learner on screen uses 20 replays and learns the optimal path more quickly. To compare our algorithms, we use two different types of mazes, a dense maze and a sparse maze. Here we plot the mean number of steps taken over time by the agent over 100 simulations. The solid lines are for the dense maze, and the dashed lines are for the sparse maze. We see that by cranking up the number of replays, we get better performance. Pseudo-rewards, denoted as F here, allow us to give hints about an optimal solution to our agent along the way. Pseudo-rewards are fake rewards that are given to the Q-learner for the purposes of updating the Q function, but do not actually confer a real reward. Pseudo-rewards have been used in the gamification literature as ways to encourage users to take paths that may seem disadvantageous at first, so that they may ultimately achieve the long-term reward. We examine here two types of pseudo-rewards. The first, based on the optimal policy as shown here, and encourages the agent to move down the optimal path. The second is an approximation based on the Manhattan distance to the goal. We see that pseudo-rewards based on the optimal policy encourage the agent to move quickly towards the goal state.
This plot shows how the agent learns. When using optimal pseudo-rewards, it converges quite quickly to the minimal number of steps. When using DINA, it converges gradually, and when using Q-learning, it converges even more slowly. For Manhattan pseudo-rewards, there is no convergence in the dense maze, but in the sparse maze, plotted with the dashed lines, there is convergence.
Next, we investigated the effects of additive white noise on our pseudo-reward methods. We found that as we increased the amount of white noise added to the pseudo-reward signal, it became harder and harder for the agent to find an optimal path.
In our paper, we explore other variants of these algorithms and how they might apply to the cognitive science literature of human learning and decision-making.
Goodbye!